This is the third video on electrostatics, and it's going to cover Gauss's law. So the chapter on Gauss's law is chapter 23. It starts off by saying that the electric field that's created by some irregularly shaped object can be the sum of the electric fields from each point on that object. We do define volume charge density as charge per unit volume, surface charge density is sigma, which is charge per unit area, and lambda is charge per unit length. We also use kind of these same variables to indicate mass per unit volume, mass per unit area, and mass per unit length doing mechanics. So you should be familiar with those three. And kind of determining the electric field of some specific shapes and doing those by integration there. We'll go through those. But it's actually, here's the electric field of a uniform disk, and we're going to go through all three of those examples. All right, electric flux is the rate at which charge is moving through a surface. And so this is the symbol for flux. It is equal to the electric field times the area. And those two variables need to be perpendicular to each other. So this would be the electric flux. It's the rate at which charge is moving through a particular area. And if you have an angle between the surface and the electric field, then because you want the perpendicular component of those, you would use EA cosine theta, because you only want the portion which is perpendicular between the two. Electric flux, again, is the charge moving through an area. And here we have a closed surface. It's got a uniform electric field running through it. And so notice that every electric field line that goes in also comes out at some point. And if you were to sum all of the electric field lines and make them perpendicular to every point on this hollow sphere, they would sum, in this case, to be 0. Flux through a cube, you only want the perpendicular portion, so you're usually going to use only two faces of that cube. But again, it's electric field times area times the cosine between the angles. All right, Gauss's law is a way to, it's based on that inverse square relationship of the force, and basically it's only going to be convenient for calculating the electric field of a highly symmetrical charge distribution. That's why when we initially did Gauss's law problems this year, we didn't want to put a square as a Gaussian surface. You wanted to make a sphere as a Gaussian surface, or possibly a cylinder around a rod, or things like that. But you want to make it a uniform Gaussian surface because it's helpful for calculating the electric field of a highly symmetric charge distribution. We come down here, we have the net flux through any closed surface surrounding a point charge is that point charge's value divided by the permittivity of free space. And it is independent of the shape of that surface because all of these lines, these electric field lines, have to go through that surface, and they will all go through it perpendicularly at some point, as long as it is a closed surface. Because of that, here we have Gauss's law. Gauss's law says that the net flux through any closed surface, which is the sum of all of the electric field lines and the area, the surface area of the entire surface, is equal to the charge inside that surface divided by the permittivity of free space. If there is 0 flux through a surface, that does not mean this part here. That does not necessarily mean that there is 0 electric field at every point on the surface, only that every electric field line that came into the surface also went out. So there are two situations where there is 0 flux through a closed surface. If there are no charged particles, or if there are charged particles but the net charge inside the surface is 0. So here, if the net flux through a Gaussian surface is 0, the following statements could be true. Which of them must be true? Well, it's not true that there are no charges inside the surface, but the net charge inside the surface has to be zero. That one is true. And the other one, I hadn't gotten to all of them, sorry, was that the number of electric field lines entering the surface equals the number leaving the surface. Oh, this is a great question. Spherical Gaussian surface surrounds a point charge. Describe what happens to the total flux through the surface if the charge is tripled. Well, if you have triple the charge, then the total flux goes up by a factor of 3. If the radius of the sphere is doubled, that does not change the total flux through the Gaussian surface. Because the same charge is located inside, it has nothing to do with the size of the Gaussian surface. If the surface is changed to a cube, again, it will not change the value of the flux through that cube. It will, however, make the math a lot more difficult, so I don't recommend drawing cubes as Gaussian surfaces. And if the charge is moved to another location inside the surface, it also will not change the flux through that Gaussian surface. So here are kind of the 4 rules for drawing a Gaussian surface. You draw a Gaussian surface if the value of the electric field can be argued by symmetry to be constant over some portion. So you can draw like a cylinder around a rod of infinite length because it's based, like the electric field will be symmetrical through every part of that cylinder. You're just not going to be going through the top and bottom of that cylinder, just through the sides. The dot product can be expressed in simple algebraic form because they're parallel, or the dot product is 0 because they're perpendicular. That's fine. You can make some surfaces parallel, some surfaces perpendicular. It's really not fun to make a Gaussian surface where you've got an angle in there for the surface and the electric field. Or sometimes the electric field is 0 over a portion of the surface. Again, Gaussian surfaces are not real. So here we have a point charge and we're going to draw a spherical Gaussian surface. If you have I want to go over this picture in just a second. But if you have a rod of uniform length, this is a good Gaussian surface because there are electric field lines through all of these sides, but none through this circular portion at the top or bottom because those are parallel. If you have planes, you can draw a cylinder, didn't mean to do that kind of goes through the center because all of the electric field is coming through this point right there. And none of it is perpendicular for the round part there. Don't use Gauss's law for things like electric dipole, which has 2 different points, and you've got all those different field lines that are bending in different places. A charged disk, again, because at the edges of the disk it gets kind of tricky, or a triangle with a point charge. And that's about it for Gauss's law. Again, I'll go through these examples of Gauss's law, or I actually would like y'all to look through them, just kind of look at them. But I'll go through them at some point too, probably in another video or recording with the iPad. I do want you to see this though. This is the electric field for a conductor. Oh, I'm sorry, it's an insulating sphere. Yeah, it can't be a conductor. For electric field inside a conductor would be 0. But for this, a uniform sphere, the electric field increases, 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 and then as you move away, we've got that kq over r squared relationship. And we determine that with a number of Gaussian surfaces. One here, one concentrically farther out, one concentrically farther out, etc. And I think that is all for Gauss's law, at least for the concepts.